Welcome to Unit 5. This is all about functions and how we can actually manipulate functions. And so we start with the idea of absolute values. Now, you've actually already been introduced to the idea of manipulating functions when we learned about quadratic functions and the fact that by changing a negative or adding a number, we can manipulate where that parabola ends up on the graph. We're going to delve a little bit further into that in this unit. So this lesson in particular, just as a kind of refresher on function notation, and it's this idea that we can have functions inside functions. So what is a relation? Well, it is two different kind of things that we can measure, but they are somehow linked, and we can create some sort of way of going between these two different pieces of information. Okay, so two different pieces of information that are linked, or two different categories, might be another way of thinking about it. So example, we can talk about fruit as it relates to color. A function is specifically a relation that has only one output for every input, or only one range value for every domain. So we see this more specifically, whereas fruit, like an apple, can be red or green or yellow or a combination thereof. When we talk about different vehicles, it's pretty standard. A car has 4 wheels. That's the end of it. Now you can get into like the fact that they're designing 3-wheeled cars and 2-wheeled cars, but for the most part, you're not going to see those on the road right now. So we're going to go strictly with a car has 4 wheels. A bicycle has 2 wheels. Don't say tricycles have 3 wheels, because a tricycle is not a bicycle. It is a tricycle. It is by definition different because it has a different number of wheels. So vehicles related to the number of wheels. If we flip that around, though, that would no longer be a function, because all of a sudden we've got, if I tell you, well, I'm driving a vehicle that has 4 wheels, well, am I talking about a car? Am I talking about a van? Am I talking about a pickup truck? Now that we've got some kind of blurred lines, but if I tell you I'm driving a car, I know I'm talking about a vehicle with 4 wheels. So that's kind of the difference between a function versus any sort of relation. It's that we can only have that one output. So we do vertical line tests to check if a function, or if a relation, is in fact a function. So we see this in our first graph. At any point, I can draw a vertical line, and it only crosses my graph at one point. Here, 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 or here. That means that for this x input, it only gives me one output. That's the only number I'm ever going to get. Here, same thing. I put this value in for x, and I'm going to get 0 as an output, always. Okay, so that means, good to know, checked, only one output. In my second graph, though, for this value of x, whatever it is, I could be talking about this point here, my positive y value, or I could be talking about my negative y value. So this is not a function because it doesn't pass the vertical line test. Okay, so we can add to this definition, check to see if it's a function. Each vertical line can only cross the graph once. So when we talk about domain, what we're referring to is all the possible input values of a function. You can even say relation. And then the range is all the output values. So when we talked about the range of a parabola and the domain could be anything. We were allowed to take any value for x, but the reality was that once we plug those values in, only certain numbers were produced for y, which meant that our range was restricted and we couldn't be, in this particular example in this graph, it couldn't be lower than the vertex. In other cases where the parabola opened downward, we would have a maximum value. So let's do a little practice. When we talk about this equation, what does it look like? If we don't recognize it, it's one of those key things we want to remember from grade 10. Y equals mx plus b is a linear relation, which means it's a line. There's no reason that I can't choose any number for x. So my domain is going to be from negative infinity to positive infinity. And remember, round brackets for values that can't be reached, and I always list my lower value first. My range then, if I plug in a really big number here, I'm going to get a really big number output. If I plug in a really small number, I'm going to get a really small number output. In general, if I wanted to get a mental picture of what this looked like, my line would look like this. It continues to infinity positively and negatively for y as well. So my range is the same as my domain in this case. In the case of B, see there. B, my domain goes from 1 to 5, inclusive. There is actually a point at 1 and a point at 5, so I can use square brackets to define those. So from 1 to 5, again, smallest to largest. My range is from -2 to +2, and so again, square brackets because it is a defined point. I forgot the negative there, always check. Make sure things make sense. Now this function is what we call piecewise. It's actually two functions put together. So we're going to have to define it as two separate pieces. It is not inclusive of -3. And we learned that that whole means not including in our inequalities unit. The filled in dot means that it is defined at 1. We say this is united with, and then we describe the rest of it. So not defined at +1 all the way to infinity. For our range, we've got, I'm assuming this is going to assume that this is 4 here. And so we'll say, and we start at the bottom, so we go from -infinity all the way up to 1. And then not inclusive, we jump from there to here and continue onward, but again, 1 is not included. We continue all the way up to +4, which is included because it's that filled in dot. So again, remember, rounded brackets are when a point is not inclusive. So infinity we can't reach, but also these holes means that we're going to use a round bracket. A square bracket indicates a defined point, so that is something where we can actually put our pen on it. So that's the filled in hole, or if it's a solid line at that point. So you might need a refresher on function notation at this point. So remember that this whole piece is your output, commonly known as y. X is your input. So when I see f of 3, and that's how I'm going to read this, what it's asking is, what is the output when the input is 3? So I'm going to fill this in and go, okay, instead of x, it's going to be 3 plus 2, which is 5, and that would be my answer. For f of 0, plug in 0 plus 2, which is 2, so f of 0 is 2. G of 2, I'm just going to plug it into function g, so that letter kind of gives it its name. That's why we've got 3 different ones here, f, g, and h, so be careful. Here I'm going to plug in 4 times 2 plus 1, all divided by 2 again. Now, I like putting brackets around anything that I'm plugging in for x. It's just a personal preference to make sure that I keep track of any negatives that might be going in there with it so that I know kind of what I've done. So I've got 8 plus 1 is 9 over 2, and I can leave it as that. There we go. G of 0 is not possible. You're like, Miss Conrad, why not? Like, 0's the best number to plug into anything, and it just gives us a value. The problem is that we've got x in the denominator. So if I did try and plug this in, it would be 4 times 0, which is nice, it just disappears, plus 1, all divided by 0. But what do we know about dividing by 0? Not allowed. No matter how many things you have, no matter how hard you try, you can't put them in 0 groups, because even if they're all spread out individually, that's still groups of 1. And if you just put them all together, then it's one big group. So no groups of 0, no dividing by 0. So this guy causes problems. And so in this case, we would call this a non-permissible value. And I'm giving you that language. It's going to show up in later units, so just kind of beware. We've got h of negative 5. I gotta make sure I keep track of what my functions are. So it's 3 times negative 5 squared minus 3. Now this square only impacts what's directly beside it, because there are no brackets around the 3x. It's just impacting the x. So I'm going to follow my orders of operation, do exponents before multiplication. So I've got 3 times 25 minus 3, which then gives me 75 minus 3, or 72 is h of negative 5. I've got f of a, so that means I just plug in a in lieu of x, so just goes in as another variable, and that's fine too. Totally allowed. H of m plus 1, so this whole thing is my input. So I've got 3 times m plus 1 squared minus 3. I'm going to expand that, so it's going to be m squared plus 2m plus 1 minus 3, or 3m squared plus 6m. That's what it simplifies to be. Finally, we've got this weird looking one, h, and that means that we're going to take the value of f, the output of f of 4, and then we're going to use that as the input. Okay, so what does that look like? Well, you could do this a couple different ways. You can either plug one equation fully into the other one, or you can solve for f of 4 and then plug that in for g. I will do it in pieces in this example, and then in the next one I will show you what it looks like plugging one into the other. Actually, I'll do it plugging in this case because it's a little bit more complicated, so it'll be interesting to see how it unfolds. So we're doing f of x into g of x. So I'm going to go 4 times, now in place of x here, I'm going to put this whole function f of x. So x plus 2 plus 1, all divided by, and again, our input is no longer just x, but f of x, so I'm going to put x plus 2 in the denominator. Now I'm going to plug in 4, because that is what x is. So 4 times 4 plus 2 plus 1 all over 4 plus 2, which gives me 6 times 4 is 24, so 25 divided by 6. And I'll just leave it as that. So g of f of 4 is 25/6. So that's if you plug one into the other and then solve it. If we do it the other way, I can solve for option A. F of -3 is, so solving for the inside, is going to be -3 plus 2, which is -1. Now, part B, I'm going to do f of -3, but that's the same as f of -1. Because all of this here is -1. And so I can go -1 plus 2, which is +1. So f of -3 is +1. And there we go. So that's what a composite function is when there's one function inside another function. So if g of x is 2x plus 1 and f of x is x squared, then when we read g of f of x in either one of these ways of writing it, that means that we should use f as the input into g. So is g of f of x the same as f of g of x? Absolutely not. If you plug in values differently, they're going to come out with different results. If we actually demonstrate this with the example here, g of f of x would look like this. It would be 2x squared plus 1. If I look at f of g of x, that would be 2x plus 1 squared, which I would expand, and that would be 4x squared plus 4x plus 1. Those two are a little bit different. So no, they are absolutely not the same. So let's play around a little bit. We've got f of g of 16. So option 1 is that we can solve this separately. So g of 16 is going to be the square root of 16, which is 4. So we've got the f4 actually is going to be 4 squared minus 5, which is 16 minus 5, or 11. And that's going to be my final answer. If I look at the second one, g of 3, Well, g of 3 is the square root of 3, so there's no simplifying that. So I'm going to be putting the square root of 3 inside a square minus 5. So that gives me 3 minus 5, or negative 2. Continuing. In general, I could write f of g of x as the square root of x squared minus 5, or x minus 5. If I use this and try and go ahead and plug that in, then I've got f. If I go directly to the simplified version, I just get minus 2 minus 5, which is negative 7. The only problem here is that this is also not possible, because negative 2, if I plug it just into g, I can't take the square root of a negative number, and so this is actually a non-permissible value. So again, we've got this idea that sometimes things don't actually work. So we need to be careful when we look at D. Negative 2 is not in the domain of g of x. That means we need to consider the domain of each original function in our new composed function, or composite function. What is the domain of f of g of x? Well, the domain of g of x is that x has to be greater than or equal to 0. So it starts at 0 and it goes all the way to infinity. So we need to find the output of f, or we need to find the output of g starting at the lowest. So the square root of 0 is 0. So that tells me that the domain of f of, first of all, I only need to look at the domain of f of x. It's a quadratic, so it's anything to anything. But because of this restriction in g, and the fact that it's the actual going to control my inputs into f, my domain of f of g of x relies on the range of g. And so what's the output for 0 when I plug it in for g? Well, it's also 0. So that means that my domain is going to be 0 to positive infinity. But all those negative values that were otherwise possible are no longer applicable because g is controlling our input. So f of x should look like a parabola. It should be opening upward, and because it's at minus 5, that's my y-intercept. It's also my vertex. So what should happen is that it should look like this. But because of that restriction of g, all of this is non-existent. And so this is my graph of f of g of x. And so all of a sudden we're controlling the domain and range. We're manipulating it by changing the function. And this is what absolute values do. This is what taking the radical of a function does. This is what taking making a rational equation with quadratics does. So, and this is what we're going to be exploring for the rest of the course. So function notation can be used no matter how the function is defined. And this is kind of the last big idea that we need to consider. So it can be a graph, it can be an equation, it can be a list, a table of values, etc. So we are given a bunch of functions here. we're told that these are specific points that define my function f. No other values can be used for function f. H is tells us that the output is twice the input. Well, that could be changed into an equation. So the output, so h of x, is twice the input. So it's 2 times x. So that's a little bit nicer to look at. The function m is defined as 4. The output is always 4. This means that we're actually looking at a scenario where we have a horizontal line. So no matter what my x value is, my y input would always have been, or my y output would always be 4. I'm going to erase those just so that we don't get confused. Okay, G is defined as this specific graph. So all the points on these lines are part of function G. And function P is defined as these specific points. And again, just like function F, we can't assume that there's points in between. We're not allowed to do that, just the points that are given. I'm going to zoom out just a little bit because I'm going to have to refer back to this frequently. So what is the output when the input is 0 for function f? Well, I look and I find, remember, when we list coordinate points, it's always x, then y, input, then output. So the input is 3, my input is 0, my output is 3. Okay, again, input of -8. I don't see -8 listed as one of my 4 possible points, so this is not possible. P, when the input is 5. So I look at function P, I find 5. My output is -4. And sorry about the typo there. And G, when the input is -1. So input again is my x-axis, and my y-axis is my output. So input is -1. Find my point that is defined by -1. And that's going to be at +3. So my output was 3. M, when the input is -100, is still 4. It's always 4, no matter what. Remember, we wrote the equation for H, so it's 2 times my input, which can be also written as -30. F of 0. So first I figure out f of 0, which I already did, is 3. Then 3 as my input would tell me that -7 is my output. Okay, so I'll let you try with H and P here. I'm going to skip ahead to this guy here. So M of all of these things. So we look at G of -2. Look there, we're taking -2 is my input. My output is +4. Okay, check. So H of 4 means that I double 4, so that's 8. But M of anything is 4, and so I get my answer there. So I could have skipped ahead on that one, but it's always good to actually check your interior functions to make sure that your inputs are all part of the domain. Okay, so we've got, this question is kind of working backwards. So we've got G of x equals 2. So what are all the possible x's? So in this case, we're told the output. And we are asked to find the input. So I go back to, in this case, my graph, because we're talking about G. I'm saying, okay, well, my output is -2, or +2 rather. That could have been gotten by either plugging in 0 or 4. So when we talk about all possible x's, that means that x can be more than one thing as long as that input doesn't match with more than one output. The outputs can match with more than one input. That's still a function. That's 0 or 4. 2 answers. This last one's going to be tricky. You're going to have to work backwards, find the inputs for G. Those will be your outputs for P, and then go from there. So in G is positive 3. I'm going to just erase that work from the previous. Positive 3. Well, we've already got one scenario with that when x is negative 1, but we've also got positive 5. So that means that P of x could have been negative 1 or positive 5. So now we need to go back. Those are the outputs. P of x is negative 1. That gives me 4 as my x value. Positive 5 gives me negative 3. So 4 and 3. Now let me just check my signs. 4, negative 3. And there we go. So working backwards, still stepwise. So you've got a couple here to try on your own. You've also got the next couple pages to give a shot on your own, but this is the definition of composite functions.